Good day, everyone. My name is Ezegloria Chidubem, a 300 level pharmacy student in the University of Nigeria, Nsukka, and I'm here on behalf of NFCPS UNN chapter, and I'll be taking you basically on some experiments in chemistry, practical. So we'll be talking about titration, and as we all know, you have been hearing titration right from your secondary school, and we have different types of titration. We have redox titration, acid-base titration, complexometric titration, conductometric titration, and so many other titration. But for the purpose of this video, we'll be talking about acid-base titration and redox titration. In acid-base titration, like you know, it has to do with an acid and a base. And acid-base titration is basically divided into two. We have alkalimetry and acidimetry. And in alkalimetry, before that, I want to introduce you to something called titrant and analyte. And a titrant is a solution of known concentration, while an analyte is a solution of unknown concentration. So for alkalimetry, the titrant is always the acid, while the analyte is always the base. And for acidimetry, the titrant is always the base, while the analyte is always the acid. So I'll be defining some terms for you. In acid-base titration, we always have the end point, and we always have what? The equivalent point. What is the difference between these two? The equivalent point is simply the amount of titrant that is equal to the amount of the analyte. That is where everything is neutralized. The amount of the titrant is equal to the amount of the analyte. But at equivalent point, you cannot just determine it by just looking at it physically. That is why you have an endpoint. At that endpoint, the amount of the titrant is slightly in excess. That is why in your acid-base titration, they always tell you that if you are titrating that, at the first color change, the observation of the first color change, that you should stop the titration. The first permanent color change, you should stop the titration so that the difference between your equivalent point and your endpoint will not be too much. And I'll also be telling you about preparation of this solution for titration. Have you ever asked yourself, okay, this solution that I'm using to titrate, how are they prepared? We have direct method of preparing the solution, and we have standardization method. Direct method is simply like, you know that most of your reagents, most of them come in solid form, like your sodium hydroxide. And then direct method just simply means that you are going to weigh out a certain amount of that compound and dissolve it in a given amount of solvent or water. If you just dissolve it, that is just the end for you. You can just prepare it like that. Why standardization? In standardization, you always have a solution of known concentration and a solution of unknown concentration. So you having a solution of known concentration and an unknown concentration, you are going to use that known concentration to standardize the unknown concentration. That's just what that standardization is talking about. So the first experiment we are going to be doing is to determine the number of molecule of water of crystallization in washing soda. You know what your washing soda is used for? You can use washing soda in preparation of your detergent, homemade detergent that you can use in cleaning your pots, your kettles, and the rest of them. So we're going to be determining the number of molecule of water of crystallization, because washing soda normally has water of crystallization. And then this is your equation of reaction. According to my manual, I have that you are going to use HCl, that hydrochloric acid is the titrant you are going to be using in the course of this experiment. And then, of course, your washing soda is the analyte, because we don't know the concentration, but we know the concentration of what? Hydrochloric acid. Remember what I told you about titrant and analyte. So I'll be using more often titrant and analyte. So the titrant here is your hydrochloric acid, and your analyte is your what? Washing soda. And then they said, according to what I have here, it says pipette out 10 ml of the above washing soda solution in 100 ml conical flask. Add 2 to 3 drops of methyl orange as an indicator. Why are we using methyl orange as an indicator? Methyl orange is an indicator used for strong acid and weak base. And you know that your hydrochloric acid is a strong acid, and then your washing soda is a salt, is a weak base. So that's why we are using methyl orange as the suitable indicator for this experiment. So titrate it with 0.1 normal HCl till a pink color is obtained. Repeat the titration, 10 ml of washing soda solution until 3 concordant reading are obtained. So you are going to do this experiment 3 times. You carry it out 3 times, then take your average titer value. Then they've already prepared the washing soda solution for you. what you just need to do is to determine the number of what water, the number of molecule of water of crystallization in this washing soda. So this is your equation of reaction, and then these are just hypothetical value. Not like you can have your own value, but these are just like hypothetical value. And then this is how your table is going to be, your burette reading, your first titer, second titer, and third titer. So this is the volume of the acid used in the course of all the experiments. So for you to get average titer, you just add 11.0 plus. You divide everything by 3 because you carried out the experiment 3 times. This is going to give you 33.3 divided by 3, which is going to be what? 11.1 mil. So this is your average titer of the acid that you used. So this is the volume of the acid that you used in this experiment. So we are going to be determining the normality of the washing soda. We want to find the concentration of this washing soda. And then for this experiment, the formula that we are going to use to determine the normality of the washing soda is this formula. N1V1 is N2 equals to N2V2. And then what is your N1? N1 is the normality of the titrant, which is what? HCl. And then V1 is the volume of titrant, which is your what? HCl. So the normality of HCl, I read it out that the normality of HCl here is 0.1 normal. And then for the volume of your HCl, obviously the volume of your HCl is going to be the volume that you got from your burette reading, which is your what? Average titer. So the volume of HCl used is this, 11.1 mil. And then for your N2 is the normality of the analyte, which is your what? Washing soda. We don't know it. And then your V2 is the volume of washing soda. The volume of washing soda, they already told you that you should pipette 10 mil from the what? Washing soda solution. So the volume of the washing soda is what? 10 mil. So what do you have to do here? You are looking for what? N2. So you just make N2 the subject of the formula. We are going to be having N2 is equals to N1 V1 all over what? V2. Where N1 is what? The normality of the HCl, which is what? 0.1. And what is your V1? Your V1 is the volume of the acid, which is what? 11.1. And then what is your V2? Your V2 is the volume of washing soda, which is what? 10. So if you check this in your calculator, I think you should be having 1.11 divided by 10, which will give you what? 0.1. It will give you 0.11111. You just write 0.1 normal. So we have determined the normality of what? Our washing soda. 0.1 normal. So we are going to continue with this experiment, because what is the goal of this experiment? They told us that we should determine the number of molecule of water of crystallization. And for us to determine the number of molecule of water of crystallization, we have to find out some parameters that will enable us to determine the number of water of crystallization. That is why we are doing these things. And then the next thing we are going to do is that we are going to find the equivalent weight of washing soda. What is the formula for equivalent weight? Equivalent weight is simply the molecular mass or the molecular weight, anyone. The molecular mass all over valency. And then this equivalent weight, I want you to listen very carefully. Equivalent weight, the formula, let me just say that it differs a little in acid, in base, and in salt. This equivalent weight, let me say that you want to determine equivalent weight of sodium hydroxide. Sodium hydroxide is a base. Sodium hydroxide, you want to determine the valency that you are going to use in the course of determining your equivalent weight. Then your sodium hydroxide, if you dissociate in water, what are you going to have? You are going to have this plus OH minus. This, if you want to determine equivalent weight, or you want to determine equivalent weight or define equivalent weight in terms of base, you can say that equivalent weight is the molecular mass over number of replaceable hydroxy ion, which is this. Number of replaceable hydroxy ion here is what? 1. This thing is 1. This thing is 1. So it's here. Here is our center of attraction. That is where we want to focus on. So this is obviously 1. And if you want to determine, let me say that you have HCl, which is an acid. If you want to determine the valency of HCl, if this dissociates, you are going to have this plus this, which is also what? Here you are concentrating on the what? The hydrogen ion. So in terms of your acid, you are going to say that equivalent weight is equals to what? Molecular mass over number of replaceable hydrogen ion, which is what? 1. So now let's talk about salt. If you're talking about salt, something salt like your sodium carbonate dissolved in water, you are going to have this. Remember, there's 2 here. So you have 2 molecules of sodium. 2 plus what? CO2. This is 2 minus. So this is your anion, and this is your what? Cation. So if you want to determine the valency of this sodium carbonate, you can either use this or use this. Remember, this charge is just plus, but you're going to multiply it with 2, which is the coefficient. So you're going to have what? Plus 2. And this one is what? Minus 2. That is the charge. So you can either use this or this. You can use the cation or you use the what? Anion. So the valency of sodium carbonate in this experiment, or the valency of sodium carbonate anywhere in the world, is what? 2. So that is it for this. The valency of sodium carbonate in your washing soda is 2. So once you determine the molecular mass of what? Sodium carbonate. Just for those that don't know it, I want to show you how you can find your molecular mass. What is the atomic mass of sodium? Atomic mass of sodium is 23. And you are having how many sodium here? You are having 2. So it's obviously going to be what? 23 times what? 2. And then carbon. Carbon is how many? 1. And what's the atomic mass of carbon? Is 12. And then oxygen is how many? Is 3. We have 3 oxygen here. What is the atomic mass of oxygen? Is 16. So this is 16 times what? 3. So if you multiply this, you are going to be having 46, and then this is your 12, and then this is your 48. If you sum everything up, it's going to give you what? 106. That is your what? Molecular mass, 106 gram. And then remember, you are going to divide this by your valency. And what did we say is the valency? We said that the valency is 2. So the equivalent weight of, don't forget, this thing. This thing is washing soda. It's not only sodium carbonate. So you're not going to leave water behind. You're also going to bring water in, which is your hydrates, because the main concern self is even water that you are even so concerned about in this experiment, because water, the coefficient of water is carrying the number of molecule of water of crystallization. So your molecular mass for water, this is 2 hydrogen. So this is 2 hydrogen, 2 times 1. And then your oxygen is how many? It's just 1, which is 16. So this is 2 times 1, which is what? 2. So this is 2 plus 16, which is 18. So you are going to be having 18. So in dividing this, you go back to your formula, which is equivalent weight is equals to molecular mass over valency. So your molecular mass for this, look at this. This is your washing soda. So the molecular mass of this is going to be this plus this. What is the molecular mass of sodium carbonate? We said that it's 106 gram. Plus, what is the molecular mass of water? We say that is 18. Please don't forget the N, because that is what you are looking for. N. You divide it by what? 2. So this 2 is going to divide everything in the numerator. If you divide this, you are going to be having 53. If you divide this, you are going to be having what? 9. Yes. So this is 53 plus 9N. That is what it's going to be. So this is actually your equivalent weight. So I don't know. Let me clean this side. So now our equivalent weight is what? Is what 53 plus 9n. Please don't forget the unit. The unit of equivalent weight is gram per equivalent, or you write it gram per equivalent like this. That is the unit. So you have found your equivalent weight, you have found your normality. We said that the normality is what? 0.1. So you are going to use this parameter to determine the strength. See, if you now want to determine the number of molecule of water of crystallization, you are going to use a formula called strength is equals to equivalent weight times what? Normality. Then always know that anytime you are finding the number of molecule of water of crystallization, they are going to give you the strength of washing soda or whatever thing you are going to work with, because you are determining, and you cannot have two unknown at the same time. They must give you your what? Your strength of washing soda, whatever thing you are working with. Okay, so this is your strength. According to what they gave us in the lab, they told us that the strength of the washing soda is 6.2 gram per liter. Strength of washing soda is what? 6.2 gram per liter. So this formula, that is strength, is equals to what? Your normality times equivalent weight. It's just very easy. You just put all your parameters in. What is the normality of washing soda? The normality of the washing soda that you got is what? 0.1. Remember what I told you about a standard solution, and what I told you, standard solution is a solution of known concentration, and what I told you about standardization, that you basically use the known to standardize the unknown. In this experiment, you can also look at it like maybe you use the HCl, the hydrochloric acid, which the concentration is known, to standardize washing soda, which the concentration is not known, because now we already know the concentration of washing soda, and if we know the concentration of any solution, it is already called a standard solution. So multiply by your equivalent weight. What is your equivalent weight? 53 plus 9n. Your strength is 6.2. So what are you going to do? This 0.1, don't make mistake. Don't use this 0.1 and multiply only 53, because this is your equivalent weight. So you're using 0.1 to multiply everything here, the entire equivalent weight. If 0.1 multiply 53, what is it going to give you? It's going to give you 5.3. 0.1 multiplied by 9 is going to give you 0.9. So what do? You make 0.9n the subject of your formula so that you can find n. 0.9 is what? 6.3. If this is coming to this side, your 5.3 is what? Minus 5.3. So 0.9 is equal, 0.9n is equal to 6.2 minus 5.3. 6.2 minus 5.3 is what? 0.9. So this is 0.9. So basically, you are going to be having 0.9n is equals to 0.9. So you make n the subject of the formula. You divide both sides by the coefficient of n, which is what? 0.9. 0.9. So this is 1. So it's that simple. So the number of water of crystallization, the number of molecules for water of crystallization is 1. And you cannot come and put 1 as the coefficient here. Is if you have from 2 and above. And then the number of molecules for water of crystallization of washing soda ranges from 1 to 10. So it can be anything. Now that the number of water of crystallization is 1, this is how your equation is going to be. Like this, because you not put the 1. So you can call this thing sodium carbonate monohydrate. Mono because it's 1, hydrate because there's water. So you can call this sodium carbonate monohydrate. So that is just it for this experiment. We have already achieved the aim of this experiment, which say we should determine the number of molecules of water of crystallization, which is 1, and that is all. And it doesn't have any unit. So we are done with this experiment.